Hello, I'm Ethan, and as you can see, my topic is simple harmonic motion, or SHM for short. But there's nothing quite simple about this topic unless you know the following information. So let's get started with our first slide, which is clues in the problem. Now there are two things that I've bolded, underlined, and put in red that clearly give a problem away for being a simple harmonic motion problem. And that is pendulums and spring mass systems. If you see or read anything in a problem about that, it's going to be a simple harmonic motion problem. Also, if you read in a problem that the system or the pendulum is oscillating or undergoes SHM, it's a simple harmonic motion problem. Now, I put an example from one of our past homework assignments that you can clearly tell it's a simple harmonic motion problem just by for the first couple words. These words right here. It says it's a mass spring oscillating system, and already you know it's a simple harmonic motion problem. And most of the simple harmonic motion problems will start off just like this. If not, they'll have a picture like one of these three pictures that clearly gives it away for being a simple harmonic motion problem. Now, for our next slide, it is relevant laws or definitions. And our first definition that you clearly need to know is simple harmonic motion. And that is the oscillation of an object back and forth about an equilibrium point caused by a restoring force. Our next definition is oscillation, movement back and forth at regular speed. The next one is equilibrium point, the natural location of an object. Also, restoring force, a force that always tries to return an object to its equilibrium point. And finally, our last definition, it is our special topic definition, resonance. When an object oscillates at its natural or resonant frequency, it experiences larger than normal amplitudes of motion. Our next slide is most common way to solve problem. And for simple harmonic motion, the most common way is to be able to determine what formula to use and to be able to determine the max and mins of displacement, velocity, and acceleration and force. For some reason, the words displacement and force are not showing up, but yes, this is the most common way to solve a problem by knowing the max and mins of displacement, velocity, acceleration, and force, and which formula to use to define the problem. And so our next slide is most common approaches conceptual. And so for conceptual problems, being able to recall the max and mins of the velocity, acceleration, force, and displacement for each change in position of the pendulum or spring mass systems is very helpful because most of the conceptual problems will be asking for either the max or min of one of these variables. And this is true for the example that I show below, where it asks, where is the block located when its velocity is a maximum in magnitude? And now, so there was supposed to be a picture that went along with this question, but I could not get a copy of the picture. So that's besides the point. Anyways, being able to recall the maximum of the variable velocity is very key for this problem and in many other problems. And our next slide is most common approaches calculation. And so for calculation problems, being able to determine which formula to use to find the variable that is asked for, whether it is the spring or pendulum period formula or the conservation of energy formula. And the reason why this is the most common approach is because in simple harmonic motion calculation problems, they will always ask for either a variable in the period formulas or energy or something like that. And so, in the example below, you know where to start with this problem because of what it asks for. It asks for the period of the system. And the system is a mass spring system. So you know you're going to be using the spring period formula. And so if this problem was asking for a pendulum and was asking for the period of a pendulum, you would use the pendulum period formula. Or if it was asking for energy, you would use the conservation of energy formula. And it's as simple as that. And so our final slide is most common approaches graphical. For graphical problems, being able to look at the graph that is given and to get the variable they are asking for from the graph is the most common approach. And the most common graph is usually a displacement versus time graph, which in the problem below, that is the exact graph they give you, but I couldn't get a copy of the graph, sadly. But there are many other graphs they'll give you, like they'll give you a energy versus displacement graph and a force versus time graph. It just depends on the problem. But you know where to start based off of that. And you would know where to start based off of knowing the max and mins, like from the conceptual problems. You use that a lot for graphical problems too. And that is it. That's my review. I hope you enjoyed. I hope it's helpful. Yeah.